Hello everyone. In 2022 at the Mertz Whitefield, astronomers using ARI discovered a peculiar new radio signal coming every 22 minutes. Astronomers were not unfamiliar with such recurring signals. These signals usually came from pulsars. Pulsars are neutron stars that emit intense light signals into the universe as they spin around their axis. However, when researchers started to examine the records of past observations in more depth, they noticed that this signal has been coming to Earth consistently every 22 minutes since at least 1988. This was a much more consistent interval than expected for a spinning pulsar, which meant it didn't resemble any neutron star we had seen before. So, where was this signal coming from? The source, named GPMJ 18390, is located about 18,000 light-years away. The signal reaches our Earth in pulses that can last between 30 seconds and 5 minutes. These pulses can emerge anywhere from 22 minutes after a previous pulse to within 6.5 minutes of the next one. While this pattern seems significantly different when compared to other signals, an interval of 30 seconds to 5 minutes is quite broad, and the more than 6-minute variance in the arrival of the pulses doesn't paint a very consistent picture of the source. However, neutron star dynamics can be very complex, and if the source really is a neutron star, many factors could affect the duration and arrival times of the pulses we receive. When astronomers examined data from the last 35 years, they could distinguish this signal from others. The researchers used this expanded dataset to average the fluctuations and determined that the source rotated every 21 minutes and 58 seconds. They calculated the energy speed and found that instead of slowing down as it emits energy into space, the source has remained unchanged for the past 35 years. This was quite surprising because normally, this energy would be expected to slow down. To explain in more detail, if the source had slowed down, its rotation period would not have increased by more than 0.28 milliseconds over a 35-year period. Otherwise, we would have detected this in past data. This is a minuscule increase and shows that the object rotated with extraordinary stability. On the other hand, this isn't too unusual for a pulsar. Pulsars can be described as the timekeepers of the universe or the clocks of the cosmos. These formations mechanically enter such a consistent cycle that they can be used to measure time across vast swathes of the universe. However, for a pulsar rotating this slowly to be this stable is indeed odd. In conclusion, to understand what makes this signal so peculiar, we need to understand how pulsars work and even precisely comprehend the cycles of these cosmic clocks. Pulsars are neutron stars we know of. Neutron stars are the remnants of the cores of dead supergiant stars, the densest objects in the universe outside of black holes. Imagine a core containing atoms similar to planets like Earth. Due to the incredible density of these stars' cores, over 99.99% of the star is essentially empty space. But imagine an entire star made up solely of neutrons found in the core, no electrons, no protons, and no empty space. In this case, even a teaspoon of material could weigh as much as 11 times the entire human population, which is about 8 billion people. A typical neutron star might have a mass about 35% larger than our Sun, but its diameter would be only as large as Manhattan Island. This means neutron stars have a level of density we can hardly imagine. Astrophysicists still have unknown reasons why this extreme environment produces an incredibly strong magnetic field. But how does all this relate to the signals from the pulsars, or the signal mentioned at the start of the video? To answer this, we must understand the complex process that generates the signal. A rain of light and matter growing exponentially can originate from a single electron. Near the magnetic poles of a neutron star, an electron can be accelerated by a magnetic field and may emit a photon called a curvature photon. This marks the beginning of a pulse. The curvature photon will move in a straight line until the angle between its momentum and the magnetic field line becomes too large. When this angle reaches a threshold, light disperses and transfers its energy to the quantum field of electrons, creating an electron next to its antiparticle, the positron. The electron-positron pair has momentum perpendicular to the magnetic field lines and can remove these lines in the form of synchrotron photons. Two synchrotron photons can create another electron-positron pair once they both reach the threshold angle between the magnetic field lines. This process repeats, increasing the number of produced photons and electron-positron pairs until the synchrotron photons no longer have enough energy to create more pairs. Afterwards, these photons move forward in space. Meanwhile, the original electron continues its journey by generating more curvature photons and more steps as it moves along the magnetic field lines. The reason why a signal from a small star remnant thousands of light years away can be detected is this pair production stage. So why do we see this light as instant bursts instead of a continuously shining light beam? This is because the magnetic poles of a neutron star are rarely aligned with its axis of rotation. This is similar to our Earth's magnetic North Pole, which is not the true North Pole around which the Earth rotates. As a result, pulsars are like massive lighthouses. They scatter light beams around the cosmos while rotating, and observers on distant planets see the beams repeatedly passing as the pulsar completes its rotation. Observations made in the Murchison Wide Field Array are a prime example. What our telescopes detect are light pulses. However, these pulses are lights in the radio spectrum with very long wavelengths, meaning they can only be detected by a radio telescope. On the other hand, the main light produced by the star is also of the same wavelength, and the peaks and troughs of the waves oscillate in harmony. Another characteristic of these light waves is their polarization, meaning they all align along the same axis. The distinctive feature of neutron stars, and what we observe in the 22-minute signal, is precisely this. The signal also features oscillations where the light's polarization axis suddenly changes by 90 degrees relative to the original axis and then returns. These oscillations last between 0.2 and 4 seconds. This effect is another characteristic of pulsars. In conclusion, most of our data points to a pulsar. However, a variable we mentioned earlier casts doubt on this theory. Yes, the neutron star's slow rotation speed, or rather the combination of the slow rotation speed with the rotation's high stability, will cause the pulsar to slow down because they reflect their powerful beams into space, losing energy in the process. Energy conservation will cause the pulsar to decelerate. Eventually, the pulsar will slow down so much that it will no longer power the pair production steps, and light emission will begin to shut down. Another crucial topic is the pulsar entering the death valley. In this graph, neutron stars are displayed based on their rotation periods on the x-axis and their change in rotation periods on the y-axis. The death valley is shown in the gray band crossing in the middle. Pulsars that have properties below this line are generally not bright. However, we see that our source is far below the death valley, which means that if the source was a pulsar, it should have been completely dark. However, we still have records spanning decades. Let's look at the positions of other known neutron stars on the graph. These formations usually rotate from 10 times per second to once per second. Our famous signal rotates at a rate of once every 1,318 seconds, which means it's 1,000 times slower than a typical pulsar. Also, if the signal starts to slow down rapidly, the data will suddenly move above the death valley on the graph. Such a rapid loss of energy would intensify the pair production phase required for the neutron star to shine. Still, the neutron star is incredibly stable, and detecting it makes no sense. Yet, astronomers who discovered the signal developed an alternative theory to explain how a neutron star with these characteristics could produce this light. In this study, it was proposed that the source neutron star might be a magnetar. A magnetar has an unusually strong magnetic field and is a neutron star whose magnetic fields are 10,000 times larger than ordinary neutron stars. It's known that these magnetars experience what are considered starquakes, which release tension from the upper shell of a neutron star. This tension can also arise from a strong magnetic field and the slowing of the magnetar's rotation. A fast-spinning magnetar star will create a bulge in the center due to the centrifugal force. Then, as the magnetar slows down, the outer layers will need to readjust and lose some of their bulge. In this case, the shell will transition to a new position, causing a temporary realignment of the magnetic fields, making it possible for energy to emit light detectable on Earth. For example, the most powerful starquake detected in 2004, SGR 180620, released so much energy that if it had occurred only 10 light-years away from Earth, it could have caused a mass extinction. So, if something could make a dead pulsar emit light, this event would be it. Could GPMJ 183910 be a magnetar affected by a starquake, or is the mystery of the 22-minute signal this? Currently, this seems the most logical explanation. However, starquakes are expected to also emit signals in the X-ray spectrum, but no X-rays are detected due to the source being approximately 18,000 light-years away. Also, it doesn't seem logical for a magnetar explosion to continue for over 30 years because starquakes are usually temporary events, and the energy runs out within a few years at most. If we're really talking about a magnetar, the fact that this signal has existed for 35 years is certainly incomprehensible. So, what could be the source of this mysterious signal? Astronomers who discovered the signal proposed several alternative explanations for the identity of the source. However, another possibility is a highly active white dwarf. A white dwarf is another type of remnant left from the recent death of a star. But this formation does not have enough mass to collapse the empty space in atoms and turn into a neutron star. Therefore, it might produce radio emissions with an unusually strong magnetic field. And since it's not a neutron star, it doesn't need to rotate as slowly and steadily as the source of our famous signal, GPMC 183910. The problem here is that this source, being a white dwarf, would need to have a much larger and stronger magnetic field than we currently know of. For instance, AR-SCO is the only known white dwarf radio pulsar, and its radio emissions are about 1,000 times less bright than the source of our 22-minute signal. So, are there any other explanations? Astronomers have observed low-frequency radio waves coming from interactions between stars and exoplanets, as well as from a binary consisting of two rotating brown dwarfs. But this emission is about 100 million times weaker than our signal's source. In conclusion, none of our theories can fully explain the 22-minute signal. As frustrating as it might seem, this is precisely the kind of mystery astrophysicists are looking for. New data that challenges long-held theories can lead to revolutionary breakthroughs in our understanding of the universe around us. Indeed, thanks to this particular case, our understanding of neutron stars is already reshaping. Nevertheless, researchers are certain that there are unidentified signals similar to this one in the galactic plane. Among the data we have collected over the years, there might be many signals similar to GPMC 1839-10A. And if records related to these signals are discovered, the processes that power emissions beyond the death dates of neutron stars will be rewritten. So, whatever might be behind the 22-minute signal, it's certain that we'll arrive at an unknown phenomenon through research. That's pretty exciting, isn't it? So, what do you think the source of the 22-minute signal could be? Please share your thoughts in the comments. See you in the next video. Take care.